All right, a little more component detail. So you thought it was bad already. Now we're going to dig deeper. All right, basic component definitions. Nominal value. 12-volt battery in your car, that's a nominal value. It should be 13.8 volts at full charge. You're never going to see that except when you first pull it off of your charger or first stop your car and your alternator has been charging it properly. But the 12 volts that we call it is a nominal value. Your radios want 13.8 volts. So the intended value of the component is nominal value. The tolerance is the amount that the value of the component can vary from the nominal value. So when you look at a spec sheet for a radio, it's going to say 13.8 volts plus or minus 5% or 5 volts or something. All right, tolerance. Temperature coefficient is another term. The amount and direction, the value of a component changes with changes in temperature. So that's how we can have a digital display that tells us what the temperature inside our radio is. We have a known one, which is called a thermistor, and we'll talk about those in a little while. Power, voltage, and current rating. The maximum power, voltage, or current the component will withstand before damage occurs. I'm pretty sure that's probably got an engineering safety margin built in, but don't count on it. Resistors and resistance. Resistance is the opposition to the flow of electrons. Converts electrical energy to heat. So when you plug in your little space heater, a coil of wire that you can see glowing on some of them, that's just a big resistor generating heat. The unit of measurement is, what do you know, an ohm. Symbol used is R. And the components that are designed to provide resistance are called resistors. So that little funny symbol is
Omega.
Omega, thank you. Kilo ohms is 10 to the third ohms, right? Because 1,000 is 3 zeros, so we 10 to the 3 for the 3 zeros. M with the ohms is mega ohms. I'm not sure why the M over here is capital and the 1 over here is not, but this is the right way to write it. 10 to the 6th. Tolerances of 0.1 to 20%. Which one do you think is going to cost more?
0.1.
Temperature coefficients can be positive or negative depending on the material. So it could be that as it cools down, it goes up or down, or it could be the other way. It warms up and it goes the opposite way. Depends on what the materials are. Positive equals resistance value increases as the temperature increases. And negative, the resistance value decreases as the temperature increases. That's pretty easy. Positive is increasing and negative is decreasing.
So as an example of why we should care, the older transceivers that had tubes and discrete components, resistors, capacitors, as it warmed up, it would drift in frequency. So you'd be tuned you'd be tuned into your net frequency, and pretty soon you were off frequency because it would be warming up.
So you would turn the radio on and then go have lunch and come back, and then it's probably pretty stable.
You'll take it up to 15 to 20 minutes, and it would start to stabilize. But you just know that in that first 15 or 20 minutes, it would drift.
Resistances range from less than 1 ohm, there's little tiny values, all the way up to greater than 20 mega ohms. And then this is an old style. You'll see one of those here, but you won't see one of those in a radio that's surviving unless it's got a lot of glow-in-the-dark parts in it. And then this is the resistor symbol for a schematic. Okay, so we had one of these we passed around a while ago. That's a resistor. Carbon composition. This is a carbon film. We're just showing you these. You're not going to probably see them. They're nothing tested unless there's some yellow up there, which there's not on these ones that are bunched up. Metal film, metal oxide film. These are all resistors. Okay, wire wound resistors. So this is the one I was talking to you about. That is got a wire wrapped around an insulator, and it's got a wiper, and that is a variable resistor, so they're wire wound. High power, they're used in power circuits The 1 watt to 100 watts plus, high inductance, not good for RF.
Anything with a coil is going to produce a field, and if you've got a magnetic field in an RF circuit, you've got an inductor. You don't want an inductor where you don't want one.
May have metal case for attaching to a heatsink. So why would you attach a resistor to a heatsink? Yes, it's to dissipate heat. Okay, resistor types. Thermistor, I talked to you about that. That's what it looks like, but that's not the only thing in there that looks like a flat pancake with wires sticking out of it. So, thermistor is a special type of resistor with precisely known temperature coefficient. Okay, remember we talked about whether it goes up or down with changes in temperature. This one goes up and down just like the other ones, but this one, we know how much it goes up and down. And of course, the more you pay, the more accurate we know how much it goes up and down. This is how we do a temperature readout in anything that's got an electronic circuit in it. So your refrigerator's got one, your radio's probably got one. Most of the radios will tell you how hot it is inside if you know where to go and look. Okay, there's both positive, PTC, and negative, NTC temperature coefficients are available and are used for temperature sensing. But look, there's no yellow, so we don't have to worry about that part, right? Variable resistors. Ah, there's yellow up there. All right, well, potentiometers. Okay, so these little guys, I can't make them out real well, but these are little potentiometers. You spin that, and it changes the resistance. And you use those for volume, turning up the speaker, or the microphone, the speaker, and things like that. Okay? Potentiometer, they're variable resistors. They're most often used as volume controls. And rheostats, materials are graphite, ceramic, metallic, cermet is what we call metallic. And there can be wire wound, they can taper. Okay, look how much yellow's up there. Variable resistors and potentiometers most often are used as volume controls. That's all you need to know.
And they will be called a pot.
But not on the test. Henry. Inductance was discovered by Joseph Henry at about the same time Michael Faraday discovered the same thing. Well, darn, now we got two guys trying to put their name on the same thing. Faraday lost out on this one. He got the farad, so they gave Mr. Henry this international standard unit of a measure of inductance. And it was named after him, even though Faraday published first. He was in 1846 to 1878. All these guys were in the 1800s, right? Late 1700s. Electricity's new in the history of human beings.
No, it's not. The recognition of...
Okay.
Sorry, I had to toss that in.
Okay, inductors. So here's some symbols. This is an inductor. The curved lines are an inductor. So that little arrow there indicates that I can spin a dial, and it's variable. It's just a plain old inductor, ferrite core, and an iron core. So the different materials for the cores, different purposes. Inductance is the ability to store energy in a magnetic field. Remember, the wire wrapped around the steel rod creates a magnet. It's storing magnetic field is inductance. Opposes a change in current flow. And the unit of measure is the Henry. And the symbol used in equations is L. Components designed to provide inductance are called inductors or coils. Inductors and inductance. So remember the coil wrapped around a iron rod that creates a magnet. That is still, without the iron rod, is still an inductor. Circular one is called a toroid, and the other is called a solenoidal. And those are small ones. You can get them really big. And then on the right-hand side there, we have what looks like a transformer to me, but it's an inductor. All right, unit measures.
You may use toroids to keep electricity from places you don't want.
Yep, or to clean it up a little bit or something. Okay, so it's measured in henries. It's less than 1. What is that little symbol?
Micro.
Dave?
That is micro.
Micro. To greater than 1 Henry. Millihenries is 10 to the minus 3. There we go. And that is 10 to the minus 6. Microhenries. Different shapes. So there's your solenoidal. That's one of the ones that's being passed around is a solenoidal. That's the one, yep, the one you have in your hand right there. And then you have the toroidal. They have different core materials, so you get a, do they call it a mixture or do they call it a composition?
Composition or soup or mixture or whatever, there's so many different ways of phrasing that.
So they're made out of different materials, and based on what the material is, affects the way it reacts. So different core materials are laminated iron. It's used in high inductance, low frequency applications such as power supply, filter chokes. Powdered iron or ferrite, and it's used in medium inductance applications. The composition or mix of materials used determines performance at the different frequencies. They have air, and it's used in low inductance, high frequency applications such as transmitting coils. Mutual inductance. There must be at least two things involved, right? If the magnetic field from one inductor extends to another inductor, then the current flowing in the first inductor will affect the current flowing in the second inductor. That's how a transformer works. We run the current through one, and it affects the current in the other because it jumps over there, basically. Creates current. This is called mutual inductance or transformer action, and it's usually undesirable. Minimizing mutual inductance, shield it with a magnetic material. Place solenoidal coils at right angles to one another. If you have to put two of these into a radio, you put one this way and one that way. If you put them both beside each other, they'll add up. Just remember the yellow stuff. Place solenoidal coils at right angles to one another. Okay, at high frequencies, interturn capacitance can become significant. Inductors can become self-resonant at high frequencies. If operated above its self-resonant frequency, an inductor becomes capacitive.
And the way that it does that is each coil is separated, is a conductor separated by air, insulator.
Or something not conducting.
So it has a built-in capacitance.
And guess what? I'll bet you capacitors can become inductors.
It can.
That's probably going to be something yellow later. We got it? Oh, Farad, the international standard unit of measure of electrical capacitance, the ability to store an electrical charge, is the farad, named after English physicist Michael Faraday. And I have a couple of devices up here that use Faraday's principle. Anybody ever seen one of these? It's a flashlight, all right? But it's dead. I believe I got it turned on the right position here. All right, open up. So when I turn this, I generate electricity, and the light comes on, and it'll run a little while. If I turn that off and crank this for about 5 minutes, I got half an hour's worth of light or something. And the way that's working is there's magnets passing past conductors in there, just like this magnet that's in here. See the magnet that's sliding there? There's a magnet here, the poles oppose each other, and then this magnet goes back and forth through this coil of wire. And I believe this one's turned on as well. When I shake it, you can see the light come on, right? Because every time it goes through there, it generates an electrical current because that magnetic field is crossing all those conductors. Turn the switch off, do this. It's got a capacitor in there that will store the power. Same thing over here for a while. Yeah, these are not high-tech, super duper capacitors that are going to hold it for a month. But if you go camping and you have one of these, you don't have to buy batteries until this little cheap plastic handle breaks. But you watch for these on sale, $2 a piece, you take 6 of them. So that's Faraday's principle and how it works. So the little magnet, this shiny silver thing in there is a magnet, and the green thing is a coil of wire. Faraday was in 1791 to 1867. He died right after the Civil War was over. Capacitance is the ability to store energy in an electric field. Capacitance is electric. Inductance is magnetic. Opposes a change in voltage. The unit of measure is the farad. Symbol used in equations is C. Wait a minute, what? C is the speed of light. Why are we doing it again? So how come we can't use I for an inductor? I don't know. Components designed to provide capacitance are called capacitors or condensers. We used to call them condensers because every car had one, because that's what stored up the power to fire your spark plug. Electrolytic, variable, it's got the little arrow through it. Electrolytic's got the gap with the curve. Non-polarized has straight line. 1 picofarad to greater than 1 farad. F is for farads. Microfarads, 10 to the minus 6. kind of the same as microhenries. Nanofarads, 10 to the minus ninth. And picofarads is 10 to the minus 12th. That's pretty small, huh? 12 point decimals to the right of the decimal point.
And talking about 1,967,482 cycles is difficult. It's awkward.
Right.
It's not a unit of measure that sounds right. 1.6 megacycles sounds a whole lot better.
It's just fractions, decimal fractions of the farad, or of the Henry, or whatever unit of measure it is, or the ohm or whatever. It's a portion of one or multiples of one. All right, converting metrics. Metrics are simple. They're so much easier than ounces and pounds. It's tens. Tens times tens is easy. Tenths of a 10 is easy. Anytime we base it on 10 digits and not some king's foot from 300, 400, 500 years ago. Convert the value to nanofarads. Nanofarad equals 10 to the minus ninth farads of a 22,000 picofarad, 10 to the minus 12th capacitor. Okay, so if we got, we're converting to nano from pico. So we've got 10 to the minus 12, and we want to convert it to 10 to the minus 9. So we're just going to move the decimals because we're not using the English system. We just move them 3 to the left. Now does the minus 6 and all that make a little more sense? Does that make it make a little more sense?
Yeah, I have that all memorized, I just wasn't sure.
Okay. Convert the value to microfarads, 10 to the minus 6, of a 4,700 nanofarad, 10 to the minus 9th farads capacitor. And the reason you're being asked this is these are questions like this on the test. They're going to want you to convert some value to
Different values, same concept. The concepts will never change.
So we're going from 10 to the minus 9th to 10 to the minus 6. So what's 4,700 nanofarads in microfarads? I heard a 4.7.
And then when you're doing the math, do you do the largest first?
It's whichever way if you're going from 10 to the minus, if we got 4,700 microfarads converting it to nanofarads, we'd go the other direction. So it's either, whichever way you're going. So if you're going from a smaller number, minus 9, to minus 6, you're moving to the left. Okay, boom, boom, boom. Three decimals. That's why this is much easier. Capacitor, 2 conductive surfaces separated by an insulator. So we've got, I don't know which one. So this one here is saying is the dielectric. That's the insulator. And that is a metal plate, and that's a metal plate. They're saying it's going to be a super thin thing. You can make a capacitor out of some aluminum foil and some saran wrap. You can make a capacitor. You're not going to make one nearly as accurately as these machine-made things, but you could make a capacitor with that. Okay. Capacitors at high frequencies, the inductance of the leads can become significant. So inductance is something that can be used to our advantage or it can get in our way. So that's something you need to be aware of, and it's on the test. High frequencies, the inductance of leads can become significant. So that's the wires going to it, okay? So you want your leads to be short. Keep that down. Effective capacitance can be reduced. The capacitor can become self-resonant, just like an inductor can become self-resonant, right?
Where's self-resonant?
Means that the inductance and the capacitance will cancel each other out and we have fewer resistance.
Some capacitors are polarized, meaning that you've got to put the juice in the right way. Positive to the positive, negative to the negative. Some don't care. Some are polarized. And for this type of the polarity of the applied voltage is important. Incorrect polarity can cause the capacitor to short circuit. Reverse voltages can destroy the dielectric layer of an electrolytic capacitor. So if you're pumping juice in and you destroy the dielectric, which is the insulator, what do you get? A short, and you got power through it, so you've got possibly a fire.
A lot of heat.
A lot of heat, That's how you'd get the fire. Hopefully you've got a fuse in the circuit, if you designed it properly. May overheat and explode even. And there's some examples of capacitors. I don't think I brought. Is there a big capacitor, big blue one in there?
And this guy right here, you see that blue line that's on the side of it right there? You can't see it from where you are, but that blue line is actually a series of arrows and a minus sign. It's showing you where the minus terminal of that capacitor is.
Simplest capacitor is a pair of metal plates separated by air. Let's pass that one around. I think we've done that already. So a set of plates separated by air. That's this little guy. And as you rotate it, the plates get more or less aligned and changes the capacitance. So there's a picture of one of them up there. It's amazing that even, when did they start making them like this? The 40s or before?
Before.
My big antenna tuner, I've got 3 big manual ones, and they've got these in them, and they're big. Types of capacitors: air or vacuum, mica or silver mica, ceramic. Oh, that one's yellow. Ceramic capacitor is on the test. Plastic film, polystyrene or mylar, paper. I don't think there's any paper ones left because they do have a lifespan, but they can be replaced with a more modern one as long as it's big enough for you to see it. Oil filled, those are fun. They'll leak, they'll catch fire, they'll do all kinds of things.
Well, that's with the transformers.
Yep.
Oh, that's PCB oils too. Electrolytic and tantalum, so ceramic and electrolytic are on the test.
And ceramic is not polarity conscious. Electrolytic is polarity conscious.
Okay, ceramic, this is the one that's on the test, and this is what they look like, those little brown things that are standing up there. And when you're in there, looking at your equipment, and they're standing up, don't bend them over. They're fragile.
Well, not only that, in an RF circuit, you bend them over, you change their orientation.
Changing something, yeah. Yeah, you will change the way the little electrons are flying around in there. They are inexpensive. Wide range of capacitance are available. Low to high voltage ratings are available. RF bypassing and filtering. So, yeah, ceramic, inexpensive. Electrolytic or tantalum. It's polarized, so don't hook it up backwards. And it's got high capacitance in a physically small size. So those are all electrolytic. Power supply filters. So these are electrolytic too somehow. Don't ask me how. I have no idea because
like that. If you look right here, you'll find a plus sign right there.
Oh, yeah.
That means this lead right here is the plus lead.
Okay. But you'll know that if you put it in backwards, right?
Oh yeah.
Power supply filters, they have low impedance AF coupling. Audio frequency?
Yep. Yep.
Okay, so here we have a vacuum or air. High voltage applications and low capacitance, and they're in transmitter circuits of glow-in-the-dark type radios.
Old glow-in-the-dark type.
World War II.
No, World War One.
Oh, one?
Yeah.
They didn't have those in the World War II stuff?
Nope.
Really? Okay, so then there's the mica silver over there on the left. It's high stability, low loss, and it's used in RF circuits, and nothing yellow up there, so it's just for your knowledge. And here's another one, no yellow, except for that picture. Plastic film on the left, you'll see those sometimes, and on the right is the paper ones that I was talking about that are now obsolete. So this is these things you might run into if you get into the niche, like Bill Meyer on the radio. He's into restoring the old boat anchors, you call
So
it.
you can take the old
You can take them out.
and put it in
And
one.
put it in a new one with the same value.
Oil filled, high voltage AC power circuits. They're oil filled, and I'm pretty sure that they are polarized.
Yes, they are.